All right, I think we're good. So it's 12:02 in Toronto, and so good morning, good afternoon, everyone. Welcome to this fourth session on the hands-on front-loading simulation. And in this presentation, we'll be looking at SimCenter FlowEFD for NX, which is a general-purpose 3D CFD tool from Siemens. And this presentation is a detailed look at the electronics cooling capabilities in FlowEFD. So we'll be focusing on electric vehicle thermal management using this FlowEFD tool. And your Maya presenter, so just a bit of an intro for ourselves. My name is Mohamed Charji. I'm a technical pre-sales specialist for Maya. I have extensive CFD experience. Before joining Maya, I used to work at Siemens Energy. And David, if you want to introduce yourself, you can do it.
Sure. My name is David Stevens, and I've been at Maya for about a year now. Before that, I worked in gas turbo machinery, turbo pump type work, and have some CFD experience in that field, as well as heat exchangers and a bit of structural analysis as well.
Okay. Great. So as for introduction to our company, so here's a brief introduction of Maya HDT for you. At Maya, we help organizations with their digital transformation journey. We are a 250% strong company, highly technical staff. 75% of us are scientists and engineers with hands-on experience in nearly every industry. And we have an interesting relationship with Siemens, where we are a value-added reseller and also an OEM. So Siemens has recognized us as their top North American partner in 2021. And we're not just a consulting and system integrator, we also develop softwares with over 30 modules authored for Siemens, used by millions worldwide. And in terms of the solutions we provide, obviously simulation is where we grew up, but over the years we expanded to nearly every other domain within the engineering digital space. So whether an organization is looking to better design, simulate, manufacture, optimize operations, so doing PLM tools, so deployment of PLM tools, namely Teamcenter, as well as AI and IoT machine learning. So we help them with that. So our combined engineering, software development, and AI expertise uniquely positions us to move our clients from concept to completion and beyond. And so, as I mentioned, we are resellers of Siemens tools. So today we're focusing on SimCenter portfolio. So the SimCenter portfolio is the simulation center. So all the Siemens tools are within all the simulation tools within the Siemens ecosystem is actually part of this portfolio. So it's basically divided into three broad categories. So CAE simulations, so everything related to 3D simulations, and also system simulation, so model-based system simulation, and physical testing. So we do all of that as part of the SimCenter portfolio. And one of the key things about SimCenter is that you can combine these different multi-physics capabilities to do like multi-scale, multi-physics, multi-domain analysis. And it's basically allows our customer to accomplish multi-physics simulation in a cost-efficient way. Today, we'll go deeper into our CAE simulation capabilities and what it can do. So there are lots of tools available for different types of simulations you want to do, so for dynamics, structures, acoustics, all of that is part of this platform. And our focus today will be on thermal flow simulation tools. And another feature of the SimCenter platform is that we have different tools for based on the user's experience levels, based on their applications. So for example, let's say for thermal flow, we have tools that are more directed towards analysts, people with extensive CFD experiences. Also, we have tools with for people with a little bit less of a CFD background and more of a CAD background, so designer level tools, and all of that is available within this SimCenter platform as I discussed. So I think it would be a good segue to launch the first poll to maybe get a sense of our audience here and see where you come from. So whether you're using CFD analysis to make design changes during your engineering process or not. So we want to get a general sense of the audience here. So and see whether you have used what's basically your CFD analysis here, whether you're using it at all or not, or which stage you're using it either it's a conceptual stage, initial design phase, or all of the phases. So we'll be sharing the results shortly. So I'm gonna wait another maybe 30 seconds or so. Now the results are coming up to see where our audience are in terms of like their CFD background, whether they're using it or not. So I think, yeah, I think it would be a good time to, I'm gonna wait another 10 seconds. Then I'm gonna share the results. All right, so let's close the poll and share the results here. And yeah, so as we can see here, so most of the people in the attendees, they haven't been using it. They haven't been using CFD tools. They're not using it currently, like 50% now. And there are some who are very familiar. So it's very interesting results that we get. So they're using it during the initial design and also all of the design phases. So 30% are responding that they're using it in all of the design phases, which is quite interesting. So I think it would be nice to hand the ball over to my colleague. I think David can, yeah.
Thank you very much, Mohammed, for the introduction. Talking about Maya and what we do here at Maya. And, based on the first poll, you can see that, yeah, we have a mix of experiences here and also a bit of differences in methodology of where CFD is implemented in your design process. And I think importantly, what we'll see today is that FlowEFD is a tool that can be used by experienced CFD users, also by design-oriented engineers and everybody in between to get useful information that can help you progress your designs to fruition. Just to mention our hands-on simulate series, this is our last of this series today. Prior to this, we did an introduction to SimCenter FlowEFD where we did a demo on IGBT cooling, which is certainly applicable to today's module as well, where we focus on electric vehicle systems. Likewise, the next one we did was on SimCenter FlowEFD for the electronic industry, where we did a detailed thermal analysis of a PCB in FlowEFD. Also, once again, very applicable to electric vehicle engineering. And then finally, our most recent webinar was on overview of HVAC simulation in FlowEFD. And today we'll be looking at the EV module. But you can certainly see all of these webinars that are live, excuse me, not live, but available on demand on YouTube by clicking the QR code. So what we'll be doing today is we'll be doing an overview of the FlowEFD electronic vehicle engineering module. So what that looks like, we'll just do a quick introduction to FlowEFD for those who have never seen FlowEFD before, and maybe just a quick overview or review for those who have seen it before. And then we'll do a quick introduction to the EV module, looking at the things that we'll be doing hands-on today in the demo. Then we'll go into our live demonstration. And from there, we will go into some of the features that I may not directly look at within the demo, but are very important in the EV module. And we'll finish up with some Q&A. So what is FlowEFD? So before we kind of jump into our demo, FlowEFD is a front-loading multi-CAD embedded CFD tool for designers. As I said, it's for designers, but it's for everyone in between, I think, as well. It's fantastic at doing quick simulations, and maybe not even some quick simulations, but really design-based simulations in a CAD environment for front-loading of your design. Front-loading is the concept of performing your simulations earlier in the design cycle to maximize the impact and catch issues before the late-stage validation. There are several features to differentiate FlowEFD from other tools on the market, and this slide aims to highlight some of these key features and functionalities. FlowEFD is a general purpose tool which can be used in a wide range of flow and heat transfer problems. We'll highlight that a little bit later. There's really not a whole lot FlowEFD can't model in terms of physics, and we'll go into that in a little bit more detail. This is specifically developed for non-CFD specialists to get fast, accurate results. And the Mesher and Solver have unique proprietary technologies which facilitate the streamlined CAD embedded analysis approach of this product. The result is a drastic reduction in barrier to entry and overall CFD simulation time. The tool is available in 5 versions to support your CAD workflow. Today we'll be looking at the NX version in this demo, but the process is identical for the other CAD systems. So what does CAD embedded mean? As I mentioned, it's CAD embedded, and it's in your CAD environment. That is really the best way to put it. Your pre and post processing is directly within your CAD environment. There's a direct link between your geometry so that any changes stay up to date. You can do direct optimization while changing the geometry. Results are shown on and in context of the CAD models. The native interface is very familiar if you've been using that CAD package for a while. And there's no need to simplify geometry or create fluid volumes in FlowEFD, and we'll take a little bit of a look at that as well later. The major CAD systems that are available for being embedded for FlowEFD are certainly Siemens NX and Solid Edge. We also support PTC Creo as well as Dassault CATIA. If you don't have any of those, there is a FlowEFD standalone version that you can use as well. And like I said, we'll be today looking at the NX version. As I mentioned previously, there's really not a whole lot that FlowEFD can't do in terms of physics modeling, and this is kind of the broad overview in this slide where you can see, I mean, it goes from very simple to quite complex physics. So it doesn't matter if you're modeling complex physics, you can do design-based analysis early on in your design for your product or whatever the application is. Even anything from even cavitation, supersonic, and even combustion is available, with everything in between, as well as we mentioned electronics, cooling. We'll be looking at joule heating today, things like that. So one of the major differences between FlowEFD and a traditional CAD workflow, major difference is the immersed boundary meshing using what are known as smart cells in FlowEFD. So typically in a normal CFD workflow, you would have your CAD geometry and you would need to extract a fluid volume. You would then need to mesh it. You'd have to put inflation layers on it if you wanted to be able to model the viscous interaction between the walls and the fluid. So then you have to worry about element quality, and if you have really small features, this can take a lot of time and really produce a very high cell count, and it can take an iterative approach to get a good model with good results. In FlowEFD, there's no simplification or changes needed to your geometry unless you want to do them for some reason. The fluid volume is automatically extracted, and it's an immersed hexahedral mesh, which makes it very robust and efficient. And all of the refinement can be done automatically if you want it to, based on gradients within the solution. Even though this might seem kind of simple and overly simplified, FlowEFD meshing is not a black box. You can do some very, very high refinement at certain locations if necessary, and tailor it to your problem's needs if you desire to do so. And really one of the big things about the immersed boundary meshing is that the way this works is that there's a hexahedral mesh that's immersed over the solid and fluid volume, and then the algorithm from there separates the solid and fluid volumes within those cells. So it automatically separates the cells into subdomains with either solid or fluid volumes, as you can kind of see here in this slide. Also, with that special technology and the immersed boundary meshing allows some pretty awesome things in terms of efficiency as well. As I said earlier, you don't need to fully resolve the viscous sublayer numerically with a mesh within FlowEFD. It uses wall functions, so FlowEFD can resolve a boundary layer with coarse or really no mesh layers. It can resolve conduction in models within just one cell, and also can resolve flow and channels over just a few cells. And it can also resolve geometry within one cell because it can divide the cell into subdomains. As a result of this, the user doesn't really need to spend much time simplifying geometry. The user spends less time for meshing, maybe sometimes only half an hour, an hour. It can take that little as a time for very simple models, or even a lot faster than that for very simple models. The mesher runs quickly because it's not trying to iteratively mesh. The solver takes less time because there are less cells required. And one of the great things is because of these algorithms is that the accuracy is not sacrificed. So this really can be a big jump in productivity. So looking at FlowEFD modules and how they're applicable today but first is just going over all these modules really quick. The new SimCenter FlowEFD module comprises various capabilities crucial for comprehensive multiphysics: thermal, electrical, magnetic, structural analysis of e-powertrain and its components such as batteries, inverters, bus bars, DC links, power modules, and their components such as IGBTs, MOSFETs, and ECUs. These capabilities include joule heating, as I mentioned, electromagnetics, low frequency, using EMAG, ECTM, the ECM battery model, which we'll talk about here a little bit coming up, electrical elements, smart PCBs, so you can bring in your ECAD data and make these reduced order PCB models using resistance networks, or even modeling them explicitly if you would like. You can also do structural analysis, which is very critical for thermoelectric simulation, being able to predict life and longevity through thermal cycles. There are 2 resistor models as well as network models for thermal heating. As I mentioned, PCB, and that you can also couple those with heat pipe compact models if that's something you need to model. And it can even do modeling of membrane and moisture for humidity analysis. And what these models that are particularly contained within the EV module are part of the EDA bridge, and as I said, heat pipes, electric, structural, and EMAG. So that'll take us into our second poll, if you want to launch that for us, Mohammed.
Yes. So yeah, actually the second poll is about, so what are the greatest challenges you face when performing CFD analysis? So if you're coming from this CFD background, I mean, there are different steps that you would go through. So there's model creation, simplification, things like that. Then there's meshing, then there's setting up the physics, basically boundary conditions. And also there's issues with solve time, like convergence issues, things like that. So maybe we want to see what would be like the main challenge when it comes like to CFD analysis in your point of view. So I mean, I'm gonna wait another couple of seconds, like 10-20 seconds, until we get more results in. But yeah, basically see what is, like, in your perspective, the greatest challenges, and that's where the FlowEFD would come from. I mean, to as David mentioned, so how these new technologies for meshing, for automated meshing, or like easier setup, I mean, comparing to other like comprehensive CFD tools, how it can help to resolve some of these challenges maybe.
Yep. And that's really one of the things we'll look at today, is you'll kind of see some of these things in our demo today as we go through in the live portion where I open up the software and work at it, is kind of how to overcome some of these challenges for yourself.
All right, I think it would be a good point to close the poll and share the results. So we can see here from the audience, yeah, I mean, expectedly, I mean, most of the folks, they seem to have problems with like meshing and convergence. Also, there's a good portion who have also their challenges is in model creation and developing boundary conditions, and less on post-processing, which is kind of expected. Yep. So yeah, let's move on with the.
Yeah. Right. So what we'll be looking at today for an example in our demo is an EV battery pack thermal analysis. And certainly this is probably one of the greatest challenges for EVs is, these really highly dense energy sources within these vehicles. And as you use them, as you remove their energy very quickly and transfer it to mechanical energy, they're going to produce heat. And so therefore, one of the big challenges here is how to keep them cool when you are discharging them as well as charging them. Because of course we want to charge these systems very quickly. People don't want to stop the EV and wait 5 hours to charge their car. They want to be able to, do it like a gas pump. We're not there yet, but we're getting a lot closer. So the goal is to assess the cooling capabilities of the coolant loop and measure the pressure drop in the coolant loop as well, because we really want to minimize that. Problem description, as I said, it's a battery pack. It contains 6 cells per module, and there are 28 total cell modules within this battery pack. Really the key takeaways here is that we're looking at this unified environment that we're describing, so the pre-post environment for CFD within NX, how to set up the battery cells using experimental data that can be extracted using testing, and also the reusability of when you're creating one of these really large assemblies is not needing to define these cells, hundreds of times to create the model. So in that regard, if we look here at the battery pack cell and module setup that we'll be doing today, the setup for the cells is that it's using data from experiments or simulations. You store the modules, these battery pack modules, as a library of components, and then you can create a pack using that library feature. One of the really nice things about this is that you can collaborate with engineers to create these models. It's not all on you. You can create this library collaboratively in your engineering system, and you can save time by reusing that data down the road. And just a little bit more about batteries here before we really jump into it. But the new battery compact model calculates the heat dissipation and rate based on the electrical or electrochemical characteristics of the battery cell. The obtained heat dissipation rate is applied to the cell. The state of charge, voltage, current, and temperature distribution are predicted. So this does require a transient analysis because these are all time domain effects. And two models are supported for batteries within FlowEFD. The first is the ECM model, which is the equivalent circuit, and second order and third order. So this is a much more compact and simplified model. But there also is the ECTM model, which is the electrochemical thermal model, which is actually looking at the electrochemical behaviors of the battery cell. Those two options are available. The ECM is probably better for a lot of people, especially a design-based approach where if you have battery test data and you want to be able to evaluate these things quickly, it's quite useful. But if you want to go more advanced, there is that option as well. So battery model extraction, how does that happen for the ECM model? The experiment consists of a charge and discharging of the battery in a specific manner while measuring the battery voltage and current. This is also done at a number of constant temperatures. FlowEFD does come with two pre-populated models for the 18650 battery. These are 18650s are very common and were used early on within the EV industry, especially in the early Tesla batteries. And as I said, why would you want to do battery model extraction? Not every manufacturer is going to give you the information that you need to do a full electrochemical simulation. And there's a lot of battery cells out there, so it can be challenging to find the parameters that you want and know that they are correct. So one of the best ways to know that things are correct is through testing. So extraction of that battery compact model really ensures that you have the proper behavior in your electrothermal simulation. So we're going to go ahead now and jump in to our demo. And I'm just going to switch my screens here real quick. And we're going to be going into the NX environment. All right. So we should be able to see the NX environment here now with our battery pack that is loading up here a little bit. And you can see what we have here is a enclosure that contains all of our 28 cells, 28 modules that each contains 6 cells. From there, you have, I'm going to hide our enclosure here. You can see that we have an inlet here where we have air flowing in that is then flowing down into this manifold and is feeding each module with cold airflow. That cold airflow is then going through the battery pack and coming out the top here, and then is being discharged out of the vehicle. So that's what we'll be simulating today. We'll be doing this in the time domain, as I said, and looking at the behavior of this battery pack over time. So before we jump into the kind of the nitty gritty here, I did do an overview of this You can also see in here, one of the important things that we'll be looking at is our contacts for each one of these modules. So we have contacts where these batteries are in series to develop around 125 volts at a full charge. And one of the first things that we really want to show is that modularity. But even before then, let's just take a quick look at our general settings, and kind of what we would do if we were setting this analysis up from scratch is the first thing we would do is go into our general settings, and today we'll be looking at fluid flow, we'll be looking at solid conduction, we will be including radiation in this analysis. We'll be doing discrete transfer. However, there are other models, including Monte Carlo. We do have some rotation in this flow, and this will be a time-dependent analysis. The only fluid we're looking at today is air. We're not including humidity, but that could be done as well. Our solid material, our default solid material, is the plastic components. So basically, one of the big things within Flow EFD is that there is a material hierarchy. So even if you do have overlapping geometry, Flow EFD can deal with that just fine by saying this material takes first priority, this material takes second priority, and if there's intersections, it will automatically deal with that. We can do wall conditions as well, default wall conditions. In this case, that will just be doing default will be smooth wall conditions. And certainly we want to set our initial conditions for the analysis. And today it's, ambient temperature, ambient pressure, and so 20 degrees C, zero velocity. We're not doing anything crazy with our turbulence parameters. And we're doing our solid parameter temperature is also at environmental conditions. So this is one of the first things we would set up if we're starting up this analysis from scratch. The other things that we have here as our basic boundary conditions, or excuse me, our solid materials first is, we have our plastic components. This does have a heat sink in this model that's not activated today. We won't be taking a look at that, but that's, that can all be combined. This includes that chip array that's within there. We do have our thermal interface copper and a PCB that's in there as well. And then our copper connections, which is a big one we'll be looking at today, all these copper connections that are connecting the individual modules. For our boundary conditions, we have just very simple environmental pressure on the outlet here, but then we also have inlet volume flow rate here at room temperature, which is 150 liters per minute. And that'll be constant. That won't be changed through the time domain. That'll remain constant. The thing that'll be changing will be the temperature and voltage in the cells and the charge level in the cells. We're not setting up any particular radiative services, but radiation is activated here, but we're not doing any type of specific emissivity or absorption parameters on any of these materials. The other big thing here is that we'll be setting up, that is set up, is we certainly need to define the contacts and where the ground, the zero voltage location, as well as the current for this analysis for the electrothermal simulation. So the first one at the positive, final positive connection of the module here, we have a current of 30 amps, and that will remain constant. You can make these transient values as well. If we just open that up, I'll show that real quick. And you can see that we have a constant 30 amps here, but we can define that as a function. More importantly though, too, we can see that this is a charge cycle and not a discharge cycle. So we could, do a discharge cycle as well, and you can say in or out. We can make it a function, and we have some goals defined here, and that's a big thing in Flow EFD is we're not really too worried about monitoring numerical residuals in the solution. Flow EFD is monitoring that for us, but we are monitoring our values that are important. So we want to make sure that the values, if we were doing a steady state analysis, would converge to a constant value. In this case, they're changing, and Flow EFD is automatically selecting the time step as well. So we have that, and then we have a zero potential location here set at 0 volts. So as I mentioned, we have our goals. We have some global goals here that are set for the entire simulation. And then we also have our mesh and we can just take a quick look at our global mesh. But we do have our global mesh here. We also have some local meshes here. So this is a fairly big problem. So we did want to define some local mesh locations, and these can be done in a variety of ways. You can do it in a box or a sphere, or you can apply it to a body. Those types of areas that are very helpful to refine certain locations, channels as well. But just our global mesh, we'll just take a quick look at those parameters. In this case, we're using a little bit of a manual mesh where we have an initial, the dark or thick outline squares are the initial mesh size, and then the smaller squares are for the refinements based on different parameters. Just a quick bit about that. If you want to know a bit more and we'll go into a little bit more detail in meshing, I highly recommend some of our previous FlowEFD videos. So finally, one of the big things that I mentioned is the modularity of this analysis. And as you can see here, we don't have any batteries defined or any of these cells defined yet. However, we have defined a cell or a module in a separate project. So in this project, we have, I'll show my cells. I'll just hide that case. You can see our conductors on these cells, but these are each one of our cells for this analysis. And so we don't have to define these hundreds of times to do this. We have to define it 6 times in one module. And the way we do that is, yeah, we have battery 1 through 6 here. And we also have 2 projects here, is because the reason we have that is that we're reversing the polarity in these cells, alternating in the packs to develop the voltage. So that's just the reason we have 2 different ones here. So about this first battery, we'll just take a look at the edit definition. And we're selecting our positive terminal or positive location, as well as our negative location. We're looking at our battery models here, and this time we're using a predefined 18650 model, and that has a specific anode and cathode chemistry. I can show you just a little bit of the details in here, which are important, where these would be in a library, and you can create your user-defined ones. But in this case, we have this NCA 18650. We have our item properties, and these R values and C values are all done using a table. And then there's the open circuit formula, which uses those tables for the final model. And we can see those curves here for all of those, looking at different temperatures and different states of charge, etc. So that's really our big one. And we can see the formula here for the entire mathematical model for the battery. We'll just close that up. But that's the model we use here. You know, if there is any type of, there is a type of, I should say, orthogonal, or excuse me, orthotropic properties to the thermal resistance, that can be defined as well. You just need to make sure that you set the direction correctly. And you can see here that we're doing 100% state of charge. And we're looking at our goals here. So we have a whole set of goals for this entire module as well. So these will be repeated once we set it up. So this is all set. We're gonna close that up. And now though, we have all of these models populated in here in our CAD environment, but we want to apply that module CFD model in here as well. And the way we do that is we go up and we go add from components, and it's already recognized all these models. We have our 28 modules. And for the first one, we would just alternate. So the first one we do project 1, second one, I'm not going to do all of these. We project 2, and then we would alternate project 1, and then finally again, project 2, and so on until we had all of our modules complete. But I'll add these first 4 so you can see them. We hit the add button and import it. It gives me a nice green check mark that it all went well. And you can see we have a from components here now. And you can see we have ECU 1, 2, 3, and 4. And each one of these has their own set of batteries, its own set of solid materials as well. And that's all automatically imported. So this is all of our setup for this project. We don't have to do anything else here in terms of defining the problem setup other than our calculation control options. In this case, that if you were to run, this thing all the way out, we've set a physical time for this to complete at 3,600 seconds. You can also do iterations. You can set, what goals do you want converged. If it's transient, you got to be careful about that because obviously not all goals are going to, go to a steady state for a transient analysis. So you have to be careful about that. We could define automatic refinement if we wanted it in a solution. That's not part of this, but that is where that would be. Solving, you can do automatic time steps or manual time steps. In this case, once the solution got going up beyond an initial transient, we stepped up the time step to 0.01 seconds. You can do nested iterations if you would like, if your numerical scheme requires that or is beneficial. Flow freezing is another thing that can be done within FlowEFD to speed up a solution. So that is used in this analysis where FlowEFD will detect areas in the domain where things have reached a steady state and will stop calculating that zone for a period of time. So you can do it permanently or periodically, and that really dramatically helps speed up the solution. So it's only looking at the transient areas of the domain for each iterative calculation. And obviously then here we have our discrete transfer radiation parameters. One of the things that's cool here, I'll mention this before we go into the results, is that you don't have to save full results for a transient simulation. You can do this thing that's called a transient explorer within FlowEFD. Then you can say, all right, I only want to save specific results, and I want to save it at this number of periodic iterations. But more importantly, you can say, I don't need all of the results to be saved for each time step. I can choose what is important. Because if you were to do all of this, it takes an enormous amount of data, especially if you're doing a large model. In this case, we're just looking at their flow parameters, mainly heat transfer, radiation, and the Joule heating is really what we care about here for our transient analysis. So that's all we're going to include. And this is where we would run our simulation. If we're going to run this, we open it up. It would need to mesh because I haven't run the full mesh yet on this demo portion. But you can run it on a cluster if you have it. There's no core limit on FlowEFD, and there's no additional license needed to get more cores. So you can choose as many as you have available. And we would run it, and then it would go into its solver environment. And if you want to see a little bit more of that, as I said, look at some of our previous webinars where we take a look a little bit more of how the solver looks as it's progressing. But today we want to spend a little bit more time on post-processing, so we'll skip that today. So assuming this, this is done, we would go to our completed solution and open this up, load up our results. We have that. We have our goals, and we'll go down to our post-processing here. So as we mentioned, we really want to look at, okay, how hot are these batteries getting? Because that is really one of the major, the limiting factor in longevity and preventing catastrophic issues with battery assemblies is temperature. So that's what we're looking at. So just in terms of, we ran this one's just run out to 1,000 seconds, and we can see first. Let's take a look at the cells. I'm just going to go ahead and first thing, just bam, hide all my geometry, and because FlowEFD will show these results right on the geometries if it's the geometry, and we'll look at our cell temps. So I have a surface plot here which is set up for looking at variables on surfaces. In this case, we'll look at the solid temperature, and it's going to open that up for us. There's quite a few cells in there, so it's going to jump through those real quick to bring them up, but still not too long, just a minute here. And I'm just going to be looking at contours, but we could be looking at isolines. If this were flow or flux, we could be looking at vectors. We could also include streamlines there as well. We can even look at the mesh resolution on these surface plots as well. In this case, we got to change our scale. and we can see the temperature distribution of all of our cells within this assembly. And certainly what we'll notice right away is that we have one, 2/3 of this cell pack is quite hotter than another. And maybe we want to investigate why that is. And so we can kind of go from there and say, okay, well, why is that part of this pack getting cooled more than this zone? And that's, something we would want to investigate. So, looking at that, we could look at the flow in a cross-sectional view of, if I just bring this back up, a cross-sectional view of what the flow looks like at the inlet and outlet of these manifolds. So let's do that. And show that. This is a cut plot. In a section view, we'll be looking at the velocity of the flow going in and out of these modules. And it's a big model, so it does take a few minutes to open up. And one thing that I really should mention, this is if you watched any of the other webinars, is that this is certainly the most complex model that we've shown on a webinar. And this probably is on the limit of what you would call front-loading CFD in a way. But also, it's important to mention is that just because this is a complex model doesn't mean it's not front-loading. Front-loading still implies that you're doing this in a CAD environment where you can make changes, where it's easy to set up the solution. This solution did take a significant amount of time to run, but it didn't need a ton of time to set this up. And that's really the big thing, is you don't have to invest a lot of man hours into these solutions to get results. Someone can set these up pretty quickly, and then you can let it run and get the results. And that's really the big takeaway here. So I'm gonna go ahead and just hide that geometry again, but you can see that this is cutting through that flow manifold. And we'll just look at that normal too. And we have our flow coming in here from the negative Z direction and the positive Z direction, and then going out the top here in the same direction. And immediately what we see, this is flow in the Y direction, so vertical flow. And what you'll see immediately here is we're getting a lot more higher velocities here down at the end of the battery pack that's being cooled more. And likely the reason for that is because we're getting a larger static pressure recovery due to the end of this tube as higher velocity flow comes in here, and the static pressure is recovered, and that's why you're getting more flow through this zone. So this is, this might say, okay, well, maybe we need to think about this and make these tubes larger in diameter if we can, to kind of slow that velocity down, so you're not getting such a large change in static pressure at the end, and maybe rerun this analysis. But that's the thing that can be done really easily, is be able to go into the CAD, make the change. You don't have to, change mesh parameters and lose all of your mesh. It'll automatically remesh it, as long as geometry hasn't been deleted, and especially if something's been parameterized, it'll automatically do it. So that's an important takeaway here. We'll go back to our results and look at some of the electrical outputs. We'll hide our cell temps here, and maybe we also want to look at the full flow here before we even do that. Is looking at the flow in the entire domain, and you can see here, yes, this is what I should have shown earlier, is that this does have natural convection coupled with it too. It's not just an internal flow. This is an internal and external flow simulation. So this entire battery pack assembly is being cooled by the ambient environment as well as these surfaces heat up. But we can see our flow accelerate in our intake here, and likewise, you can see here, yes, that there is, quite a bit more flow going through here, and yes, the velocity is decreasing here and getting more static pressure, so you're getting more flow through these cells for better cooling, and that's something that probably should be looked at, unless that's within the temperature difference wasn't enormous, and you're saying, okay, I'm in within a few degrees across my cells, I'm calling that good. That could be as well. But let's look at some of the electrical properties. If we can show So we want to look at the voltage on the copper connections. We can do that here. And as you can see, we have essentially a 0 voltage here down at our boundary condition for a 0 potential. And then we have the voltage that is calculated from the battery model and the current down here at this location, which is 126 volts. So we can see that. Maybe we also want to look at the copper current density and really see, make sure that we're not overworking any of this material for a current. And we have, we're showing, so one of the nice things about FlowEFD is that once you create one of these plots, you don't have to go in and re-edit the definition to change the variable. You can just do this drop down, which is really nice, and we'll just look at electric current density here. And we can see certainly, our mass, peak density is in these crossover connections here, where these are all taking the 30 amps of current. So that's going to be where some of the really high locations are, as well as some of these changes here. So we can look at that. As I said, it's really easy to change these. Maybe the last thing we want to look at is the module temps, so the casings of those modules and what temperatures those are reaching. And so we'll go ahead and show those. That could be rather important, making sure we're not hitting the limits of our casing material. It would obviously be very important to not have any type of escape, of our cooling flow. And obviously, if these were, looking at the cell temperatures, we obviously wanted to make sure that we're not compromising the battery casing as well. And this is just taking a second to open. And I'm just going to keep an eye on the time here, because there is a few more things that I want to show in our slideshow, as well as some of the results here. And there we go. It's just a really big plot. And may have to edit some of our contours here. But we want to look at the entire domain here of these battery casings. It's just a little slow for me right now. And we'll change the range on these. And it is a little slow because this is a big plot. And I may actually have to, let's see what's clear and hide. And just show again. Sometimes that speeds it up and takes care of things. Yeah, there we go. So you can see the temperature of all of the casings here. Really nice resolution. You can see the imprint of the cells heat coming out here in the sides of the casings. And really our highest temperature locations is at these contacts. We've got some joule heating going on here. And but overall, not too bad. We can also probe if we want and really look at detailed locations. And we can see that's 31C down there. Just speeding it up here a little bit because we want to be able to see the rest of this stuff. So I'll hide this guy. Flow trajectories, really easy to do. This one's kind of coarse. Maybe we want to make sure we don't have any nasty eddies in a certain location. And it looks like we're getting a little bit of an eddy here at this outlet, and maybe we want to correct that. Jumping along here, surface parameters. We wanted to see the static pressure outlet for this assembly. That was one thing we wanted to calculate, and really there's not a whole lot of pressure drop for this at this flow anyway. And lastly, or two things actually, let's look at our goal plots. And these are very important to see, especially if we want to look at individual battery packs within this. We can look at our goals and how they change through the transient solution. I'm just gonna hide all these, but let's say we want to look at, these are all state of charge. Current is going to be constant. Let's look at this solid temperature here. Let's just say we want to look at this and show that really quick. It's going to show a summary first for the maximum value over time, minimum value over time, but we also maybe want to see a history, and we can see that that's not quite linear increasing, but increasing over time, which is what we would expect it to see. So you can plot these as a function of time. You can export them into Excel in a matter of seconds, and it gives you the nice chart as well as a plot, and you can export these all at once if you want, which is extremely useful. We'll hide that. One of the last things I want to show, and this is kind of a new powerful feature within FlowEFD, is something called flux plots. And for any type of like electronics heat transfer, where you have a bunch of components, this is really useful. So in this case, we'll say use all components, but basically it's going to give us a nice flow chart of where all of our energy, our thermal energy is going and how much of it is going to each component. And let's get that coming up. It's just going to take a second to load up. So it's going to make a nice flow chart for us. And this is going to start out being quite large. And maybe I actually want to just go down to one component is probably a better idea to start at, because this has a lot of components. And you can go that fine if you really want to. Of course, it doesn't like that I did that. It's going to want to calculate all of those components, which it can do. It just might take a minute. All right, here we go. So let's grab one of these cells, and let's look at one of those. And let's just grab one of these cells. All right. This will be much more manageable. Trying to look at this all in the context of itself would be probably a little bit much for what you would want to use this type of tool for. Kind of probably wouldn't be able to see the forest through the trees per se. We can filter things out by size, and it's maybe I can get this to redraw. Here we go. And so it's going to give me a flow chart here. So it calculates. I'm going to resize this, but it's going to give a flow chart. I can change this to include certain elements and do that. It can also include boundary conditions, whether it's thermal effects, whether it's Joule heating, and these can all be included in the flow chart. I can select certain locations within here, and there we go. Resize this, and I can see all of these different ones. So if I'm looking at each cell which is included in here, I can see that, and I can see the temperature of each cell, you know, what it is at current time, what it is at a maximum time, etc. But I won't dive into too much more of this. And you can see there's vectors going from where the heat is coming from, etc. So we'll go ahead and close that up. Don't want to take too much more time. Just the last thing I do want to show, which is really powerful within FlowEFD, and this can be kind of tough to do within some other tools, is there's something called the Transient Explorer, as I mentioned, that you don't have to change and show all of your data. You don't have to save all of your data at every time step. And likewise, it's really easy to produce transient plots within FlowEFD and animations. So I already have these plots that are produced, but when I open up the Transient Explorer, it loads up all of that information. And just a perfect example here, I'm just going to hide this so it's easy to see, and then I'm going to open up this transient plot, and let's look at that in that cell where I kind of cut things down a little bit. and we can create a really nice time domain animation with this. Oh, we got to change that. And we can see how this all changes over time. This reaches steady state pretty quickly, but you can see some small changes in here. But it's nice to be able to make these transient plots. I can export this as an animation really quickly, and it's very efficient. So not needing to load up all of that data for each time step to create an animation is really powerful. All right, I'm going to jump out of the tool now and go back to our presentation and go ahead and jump back here. And so we're going to skip our third poll though, just before so we can get finished up here and get some Q&A in. Just want to mention some of the things that are available in here that I didn't cover directly. Certainly, e-powertrain thermal management, charging is something else we could model. You do have the ability to even model IC packages directly within FlowEFD using the package creator, and that can even create really explicit models for those packages if you're worried about IC temps and very fine details in IC temps. Moving on to the next, there is plugin for electromagnetics, which is extremely important for EVs, as well as I mentioned earlier, the thermal structural analysis is available. One of the great things that I just want to mention is that certainly EVs, I think, are a perfect example of the requirements for multi-physics simulation. If we're looking at this Tesla Model S inverter here, you have everything going on here. You have IGBTs, you have bus bars where you need to maybe look at an EMAG analysis, your DC link capacitors. So you have thermal, electromagnetics, flow. It all needs to be cooled, and it's all in one coupled package. So it really matters everything that's going on, and of course PCBs in there as well. This is an example from a customer that was designing an electric motor. This shows their data, their FlowEFD results, first their measured results, and as you can see, they came out very nicely. FlowEFD does have the capability of doing 1D elements, so if you're doing natural convection and you really want to cut down on your cell count and you don't want to 3D model all of that domain, you can do 1D elements to speed that up and just keep it to most of the solids for 3D elements. We do have the ability for design exploration and optimization. This is also highlighted in some of our past webinars, so I won't jump into this too much for time reasons. And also, you can use FlowEFD to create a reduced order model using an FMU that can be imported to AimSim for faster simulations and doing that in the future as well. And we'll jump into our fourth poll here.
All right, thanks, David. Yeah, so our fourth poll is the preferred topic for an upcoming webinar. So this was a pretty complex model that we did with the FlowEFD, as you mentioned. So it has electrochemical modeling, it had the thermal flow, all of that. So as we mentioned at the beginning, so there's also other tools that are available within SimCenter portfolio. So we just want to get a sense of what would be a topic of interest for the upcoming webinars, whether it's code simulation. So as you mentioned, reduced order modeling with the tool like MSIM, or 1D tools, or design optimization, exploration using heats, or other tools that we have within the portfolio. So StarCCM Plus are the most comprehensive CFD tools for turbo machining applications and all that. So just gonna give it a few more seconds and then close and share the results, I guess.
Yeah, and this is certainly information we like to hear from everybody, because
yeah,
we want to do webinars that people want to watch,
and exactly.
that are helpful to people.
Yeah.
So we really appreciate your input.
Yeah, looks like majority of folks are very interested in heats and star, all the portfolio, less on the additive side, but okay. So that's very good information for us to plan the next webinars. And yeah, we can go on with
So just a quick
Yeah.
mention, I mentioned this earlier, these are our past webinars. So please, follow the QR code or go to our YouTube page to find these. Really easy to find, and you can find out some more details on meshing, optimization, the solver, etc. in those. And in our last poll, just a little bit more information to help us out.
Yeah, so actually there are different ways to connect. I mean, if you're interested to learn about FlowEFD, so it's basically your answers will help us out to follow up. I mean, there are a couple of questions on, people are asking if we can send the replay of this today's webinar or share the PowerPoints. Yeah, I think the recording will be available on demand after the webinar. So also, if you have any questions, we can follow up definitely. And
Yeah. All right.
all right, so I guess
All
I'm
right.
gonna wait a couple of more seconds and then close poll. Yeah, looks like we're even between the options here, so people are
Yep.
interested in all of these options, which is
Yep.
quite interesting.
And that's what we're here for. As pre-sales engineers, we're here to answer your questions and help you find solutions to your technical problems. And that's what we're here for. I want to thank everyone again for their time. I'm happy. I know it's 1 o'clock. I'm happy to hang out for however and for a few minutes and answer any questions that you have. Please feel free to pop them in the chat. Also, if you have a more complex question, my email's right here. Please feel free to contact myself or anyone on the marketing team, and we'll be happy to help you out.
Exactly.